Great. Welcome, everyone. So for the Pico-Seminar today, this is a part of the Pico electrodynamics theory network where we are trying to bring in theorists across working in the topological physics, quantum optics, and Casimir physics, and also the vacuum and thermal fluctuations, really looking into the microscopic phenomena which occurs in the picoscopic scales. So today we have Professor Bradlyn from University of Illinois as our speaker, and now Professor Zubin Jacob will introduce it.
Great. Thank you so much, Satwik. It's a real pleasure to introduce Professor Barry Bradlyn. He has made many important contributions in the theory of topological materials. And just wanted to tell you a little bit about him. So he is currently an assistant professor in the physics department at UIUC. And he received his bachelor's in physics from MIT in 2009 and went on to receive his PhD in physics from Yale University in 2015. So his thesis work is actually something that our group over here has also followed closely, which is focused on Berry phases in the quantum fractional Hall effect, and also multiple different ways of looking at the viscoelastic and thermal response functions for two-dimensional topological phases. So he's also held a postdoctoral research position at the Princeton Center for Theoretical Sciences, where he studied the role of crystal symmetries in topological insulators and semi-metals. So we are really looking forward to his interesting talk on topological crystalline insulators. And we also hope to talk to him about his work on Hall viscosity and other important ideas to which Barry has contributed. So without any further delay, we welcome you and we look forward to your talk.
Great, thanks for the introduction and for the invitation. So today I want to tell you a little bit of a newer story on some progress we've made in trying to understand the bulk response functions for topological crystalline insulators, separate from their surface physics. So this is work that most of the new results we just recently posted in this paper here. And this is a collaboration with myself and on the theory side, Ben Weider and my student Kwansen Lin at UIC, Greg Feet and John Palumbo as well. We had computational help from Xiaopeng Guo and Zijun Wang and Jeremy Blackburn, Binghamton. And we've talked with experimentalists at UIUC about the potential implications for some of these results. So as an outline, I'll start with a bit of a review and background on topological insulators and topological crystalline insulators. And then I'll dive into what we know about topological crystalline insulators with gapped surfaces. I'll start with an introduction to magnetic Axion insulators, which I think are the most well understood case. And then I'll talk about some of our new insights into bulk probes for non-magnetic topological crystalline insulators. And I'll introduce, or I guess reintroduce, an idea from about a decade ago on spin-resolved topology of electronic bands. Okay, so symmetry and topology are two areas of mathematics that really come together in the study of topological materials. Symmetry constrains the local properties of electronic structure, and it enters into material science through the crystal symmetry group of given crystal. So we have our 32 point groups and our Bravais lattices that give us our 230 space groups, and electrons move around in potentials that are constrained by these symmetries. Topology, on the other hand, is the study of more global properties, not necessarily local constraints on the system, but it's the study of the global properties of functions. And topology really tells us about divides functions into different classes, whether or not they can be smoothly deformed into each other. So the typical example is we have a sphere and a donut, and we can't continuously deform a sphere into a donut without cutting the sphere in some way. In physics, I think one of the first places topology really entered was in fluid dynamics and the study of the stability of vortices. And vortices like this are stable because the velocity field has some non-trivial winding around this torus. So how does topology enter into the study of electronic systems? Well, it enters because the wave function in an electronic system is just as much of a map between two spaces as the velocity field for that vortex. In a crystal, Bloch's theorem tells us that our wave functions are parameterized by some momentum in the first Brouillon zone. And we can think of the set of occupied band wave functions in an insulator as a map from the first Brouillon zone to some space. And it turns out that this map can be topologically non-trivial. The simplest example is in 2 dimensions, where if for a 2-band system, the occupied wave function takes a point in the Brouillon zone and maps it to some point on the Bloch sphere. And so that mapping can either not wind around the Bloch sphere, all of the wave functions point in the same direction, or it can wind some integer number of times. And that winding number is a topological invariant called the Chern number. We can't change this integer continuously. If we want to change the integer, the Chern number from 0 to 1, we have to do something drastic. And the analog of cutting the donut. In an electronic system, the analog of cutting the donut is to close a gap in the spectrum so that we don't have well-defined occupied bands anymore at some point. So what this means is that if we have a topological insulator, which I'll say is a system that has some invariant like this not equal to 0, and we have a trivial insulator, we can't continuously tune the topological insulator to the trivial insulator as a function of, say, this position y. Something drastic has to happen at the boundary. And that drastic thing is that a gap closes and we get some boundary metallic states between this topological and trivial insulator. So that's the story of topology without symmetry. But we can ask, what does the topology of electronic band structure really mean about position space local quantities? What's it telling us about the atoms in the system? Now, we know from de Broglie and Bloch that electrons in solids occupy Bloch waves. They're extended over, the energy eigenstates are extended throughout the crystal. So if we want to ask a question about where the electrons are really living, we need to do a Fourier transform. We need to go from this Bloch basis to what's called a Wannier basis, which is localized in position space. So in 3 dimensions, we want to try and localize these Bloch waves in all 3 directions. It turns out it's always possible to localize Bloch waves in one direction and form what are called hybrid Wannier functions, which are localized in one direction, extended in the 2 other directions, and are functions of 2 momenta, which I'll call k perpendicular, and 1 position, Rn, the center of this localized wave packet. And the centers, Rn, can depend on these momenta. So if we want to understand if we can take these hybrid Wannier functions and localize them further, we should see how these centers depend on momentum. Now, it might be the case that these hybrid Wannier centers are most nearly independent of momentum. And in that case, we can do a Fourier transform in 2 other directions, or in this example, 1 other direction because it's 2D, and get nice exponentially localized Wannier functions that describe our occupied states. And that's what happens in a trivial insulator. It could also be the case, though, that these hybrid Wannier centers wind throughout the unit cell as a function of momentum. So at momentum 0, they're centered at the origin of the unit cell. And as we vary the momentum, the hybrid Wannier centers move up and up and up. And then at momentum pi, they're localized at the origin of the next unit cell over. So there's a flow of Wannier centers. And in that case, if we try and Fourier transform these hybrid Wannier functions as a function of this momentum ky, we run into discontinuity. There's a branch cut in this function when we go from one unit cell to the other. And this manifests in power law localized functions rather than exponentially localized functions. So the topological invariants that we can compute for electronic band structures are really telling us about obstructions to finding position space localized Wannier functions that are exponentially decaying in all directions. When we add symmetry into the mix, it does two things for us. So the first thing is that symmetry just gives us some tools that we can use to identify topologically non-trivial phases. But symmetry can also protect new topological phases that we can't get without crystal symmetry. We can take this observation that I just made that topological insulators don't have exponentially localized Wannier functions, and we can expand it a little bit to include phases protected by a symmetry. So I can say that I can define a topological crystalline insulator to be a system that doesn't have exponentially localized Wannier functions that also respect the crystal symmetries. By breaking a crystal symmetry, I can make exponentially localized Wannier functions. So this sort of umbrella of tools for using symmetry tools to diagnose topological phases goes under the umbrella name of either topological quantum chemistry or symmetry-based indicators. And it gives us a way to use symmetry data of the occupied wave functions to determine the topological properties of the occupied bands. What we can do is look at all of the different ways that we can place trivial localized atomic orbitals in a symmetric way in a crystal. Since each of these configurations canonically has exponentially localized Wannier functions just given by the atomic orbitals, we know that the set of the set of representations of the symmetry group at each point in momentum space that we get for an atomic configuration is consistent with a trivial insulator. And so any set of configurations of symmetry representations that doesn't appear in this list cannot be trivial. It has to be topological. And we can use this to classify topological phases in all 230 non-magnetic space groups and even all 1651 magnetic space groups. So that's how we find and diagnose topological insulators. But what do we really do once we have a topological system? What can we look for? So the canonical example that I want to start with here is a 3D strong topological insulator protected by time reversal symmetry. These were introduced by Foucault and Meillet. And in these systems, the sort of first experimental confirmation of a strong topological insulator came by looking at the boundary states. These systems have an odd number of twofold degenerate Dirac cones in the surface Baron zone. So the surface Baron zone has two momenta, let's say kx, ky. We get this twofold degenerate Dirac cone. And you can see it in experiment here. So we can use the theory of symmetry-based indicators to tell whether or not a system with inversion symmetry is a 3D strong topological insulator or not. All we have to do is look at the parity eigenvalues or inversion eigenvalues at each high symmetry point in the Baron zone and count them. And Foucault and Meillet told us that if the total number of parity eigenvalues over 2 is odd, then the system is a strong topological insulator. Now, there's more to the story than just this Dirac cone on the surface, though, because it's been long known in high energy physics that if you have a single twofold degenerate Dirac cone in a two-dimensional system, that this system actually spontaneously or anomalously breaks time reversal symmetry. This is something that's known as the parity anomaly. Now, our 3D strong topological insulator is time reversal symmetric. So something has to give here. Time reversal symmetry is still there, but what happens is that time reversal symmetry on the surface is restored because the bulk is actually non-trivial. The bulk of a 3D topological insulator has a non-trivial electromagnetic response governed by this Lagrangian here, theta E squared over 2 pi h E dot B. So if I look at E dot B is odd under time reversal symmetry because E stays the same and B reverses sign. So classically, you would say that in a time reversal symmetric system, this coefficient theta would have to be 0. But quantum mechanically, we know that it's not the Lagrangian that enters into the dynamics, it's the action. And for the action, it's not the Lagrangian that enters the dynamics, it's the exponential e to the I times the action. And for that to be time reversal symmetric, we just need e to the I times the action to be real. And it turns out that we can have that with theta equals pi. In that case, e to the I times this electromagnetic Lagrangian is equal to 2 pi, or is equal to an integer, because the integral of this E dot B is equal to an integer. We can compute theta for a 3D topological insulator in the bulk using the Berry connection. It has this formula here in terms of Chern-Simons form. Now, the interesting thing is that since the bulk of a 3D TI has theta equals pi, that means that we can break time reversal symmetry on the surface of a 3D topological insulator, and that gaps the surface Dirac cone, but there's still some non-trivial dynamics in the problem from this bulk electromagnetic Lagrangian. What it means is that the surfaces of a 3D topological insulator, if they're gapped, actually have a half integer Hall conductivity. And this leads to a magnetoelectric effect, where if I apply a magnetic field in the z direction, let's say, then a Hall current flows. Well, let me do it the other way. If I apply an electric field in the system, then a Hall current flows on the surface and generates a magnetic field. And the reverse process can also occur. This was actually measured experimentally in terahertz spectroscopy for a gapped topological insulator and a magnetic field that gaps the surfaces. So that's the story for 3D strong topological insulators, and we understand it quite well. There's surface signatures of topology, there's this bulk Axion electrodynamics, and there's symmetry-based indicators that we can use with inversion symmetry to tell us that theta equals pi. Now, recently, there's been sort of an explosion in the zoo of topological crystalline insulators that can exist. There's systems that have multiple Dirac cones stabilized by extra symmetries like mirror symmetries. More interestingly, there's been the introduction of what are called higher order topological insulators, which actually don't have protected gapless states on 2D surfaces, but in highly symmetric geometries have 1D chiral or helical hinge states around some crystal symmetric contour in the system. So with inversion symmetry, you can have a hinge state around this great circle in a spherical system. There are so-called rotation anomaly insulators that have surface states on surfaces that are perpendicular to a rotation axis and hinge states on the other surfaces. Now, many of these are diagnosable by symmetry indicators. I can give you a space group and tell you what characters of symmetry elements compute at all of the high symmetry points and tell you that you are in one of these higher order topological phases. But aside from hinge states, currently there's not much known about what is going on in the bulk or the surfaces of these systems. Now, this is a bit of an experimental problem. The problem is that hinge states are not a very accessible indicator of topology in an experiment. And the reason is hinge states are very sensitive to surface disorder. If I have a 3D higher order topological insulator with some hinge state, anytime I have, say, a stacking fault or an extra layer on the surface that can change where the hinge state propagates, I can have puddles or islands of hinge states that go around in a circle. And so doing an ARPES or STM experiment to identify these hinge states can be problematic. The situation is even worse because if I don't have global crystal symmetry for the entire system, which I never do in a real system, I can actually gap the hinge states without changing the bulk topology at all. I can take my higher order topological insulator with hinge state configuration like this, and I can glue 2D topological insulators to the surfaces. And I can do this in a way that gaps out all of the hinge states. So this sort of leads to the question of what are the robust observable signatures for these higher order topological insulators? So in this talk, I want to focus on inversion symmetric higher order topological insulators. These can be understood by starting with a 3D TI and either breaking time reversal symmetry in an inversion symmetric way to get a chiral higher order topological insulator, or superposing 2 copies of a 3D TI to get a helical higher order topological insulator. So since I can gap the hinge states in such a system, the question remains what's left. I'll start with the magnetic case first, because there we actually understand the story quite well. If I have a magnetic system, if I take a 3D TI and I gap it with inversion symmetric magnetism, it actually turns out that not much about the bulk changes at all. Because this E dot B electromagnetic Lagrangian, not only is it odd under time reversal symmetry, it's also odd under inversion symmetry, because E changes sign under inversion and B does not. And that means as long as I preserve inversion symmetry in the bulk, if theta was pi when I had time reversal symmetry, it's still pi when I break it. All that I do when I break time reversal symmetry then is I gap the surface Dirac cones of the system. And then I get gapless surfaces or gapped surfaces with half integer Hall conductivity. And these systems go under the name of magnetic Axion insulators. It turns out I can actually construct a magnetic Axion insulator in a slightly different way that gives me a good picture of where this theta equals pi is actually coming from in the bulk. What I can do is look at the hybrid Wannier functions for the magnetic Axion insulator. To do this, I can compute the non-abelian Berry phase for the occupied bands. And I find some Wannier centers that look like this for some particular model, but the behavior is more or less generic. What I find is I have some Wannier states that are centered around 0, which here means the origin of the unit cell, and some Wannier states that are centered around pi, which is the boundary of the unit cell near A/2, where A is the lattice constant. And I can divide my Wannier states in half. Half of them are into 2 groups. One group that lives near the origin of the unit cell and one group that lives near the boundary. Then what I can do is I can compute the Berry phase just for that each group of Wannier functions separately. This goes under the name of nested Wilson loop sometimes, but really what it is the Berry phase for the states in the hybrid Wannier, for the hybrid Wannier states localized near one of the 2 inversion centers in the unit cell. And what I find for a magnetic Axion insulator is near the origin of the unit cell, the hybrid Wannier states have Chern number +1. Near the boundary of the unit cell, they have Chern number -1. You can see that in the windings of these nested Wilson loops. What this means is that I can make a system that's topologically equivalent to a magnetic Axion insulator as an inversion symmetric stacking of Chern number 1 and Chern number -1 layers. I place a layer with Chern number 1 at the origin of each unit cell, a layer with Chern number -1 halfway across the unit cell at the boundary, and I tile this throughout space. From this layer construction, we can sort of see why an Axion insulator has to have theta equals pi. I can make a finite slab with one of these layer constructions, in the bulk, there's an equal number of Chern number equals +1 and Chern number equals -1 layers. So the bulk Chern number is 0. But at the boundary, I end up with an extra half of 1 layer if I do things in an inversion symmetric way. So I get in an inversion symmetric system, one surface with Chern number 1/2 and another surface down here with Chern number 1/2. And this system actually has hinge states, because if I draw it, this has Chern number 1/2 with respect to a normal vector going this way, which means it has Chern number -1/2 with respect to this normal vector, or the outward pointing normal. And that means I have a Chern number difference of 1 across the sphere, and I get a gapless hinge state. And I can get rid of this hinge state by gluing one Chern insulating layer to the top surface. This breaks the global inversion symmetry. And then I have a surface with Chern number 1/2 and a bottom surface with Chern number -1/2. These half integer Chern numbers in a gap system tell us that we have a bulk axion angle theta equals pi. This implies a surface anomalous Hall conductivity in a magnetic axion insulator. It implies a non-trivial magnetoelectric effect. And it also implies that if I insert a magnetic flux quanta through this system, that I'll bind an E/2 charge that on average lives on, or I'll bind on average an E/2 charge on each surface, is the way to say it. Okay, so using the magnetic space group extension of these topological quantum chemistry tools, it turns out we can show that all chiral high order topological insulators have theta equals pi. So we understand the bulk of magnetic or of chiral high order topological insulators. So now let's try and do the same thing for helical high order topological insulators. And there we run into a little bit of a problem. If I just take 2 copies of a 3D-TI with inversion symmetry and superimpose them, then I get theta equals pi plus pi, which is 2 pi. But it turns out theta equals 2 pi is gauge equivalent to theta equals 0. So learn nothing about the electromagnetic response that way. Naively, a 3D-TI isn't layer constructible. So just by taking 2 copies of it, I can't necessarily layer construct a helical high order topological insulator. But it turns out in a lot of cases I can. And to see that, we can look at the Wilson loops, or the hybrid Wannier centers, for a helical high order topological insulator. Again, they generically divide up into 2 groups. One group centered near the origin of the unit cell, one group centered near the boundary. And if I look at this nested Wilson loop again, what I find is that each group of Wannier bands has a non-trivial 2DZ2 invariant. So each group of Wannier bands describes or is equivalent to a 2D time reversal invariant topological insulator. And this gives me a layer construction that looks like this. I have a 2D-TI at the origin and a 2D-TI halfway across the unit cell. Now this is good, but each 2D-TI is in principle identical. Like, all I know is that it's a 2D time reversal invariant topological insulator. So from the looks of it, it seems like I've just constructed a weak TI. But there's something more subtle going on. And to understand that, we can look at a different way of splitting the occupied states in half that's sort of inspired by some old work on the quantum spin Hall effect. So even in systems with spin orbit coupling that don't have conserved spin, there's still a meaningful way to talk about the spin of occupied states. What I can do is pick a spin direction, call the spin along that direction S, and I can project the spin operator into the space of occupied states. My projector onto occupied states is P. I look at the operator PSP. I can diagonalize PSP. If spin is conserved, it has eigenvalues that are just equal to plus or minus 1. I'm going to set h bar over 2 equals 1 for the sake of simplicity here. If I don't have spin conservation, so if I have a SOC, then the PSP eigenvalues aren't necessarily 1 or -1, but it still may be the case that there's a gap in the spectrum of the spin operator. And if there's a gap, then I can consider separately these upper and lower spin bands, and I can compute topological invariants for those. In 2D, the topological invariant I'll want to focus on is the Chern number. And this gives me a way of writing a 2D system with spin-orbit coupling in terms of Chern insulators for the upper and lower spin states. For a 2D TI, whenever a spin gap is open like this, I can compute the partial Chern numbers, I'll call them, of the upper and lower spin bands. And what I find is that a 2D TI always has these C+ and C- equal to opposite odd integers. So for a 2D system, C+ mod 2 is just our 2D Z2 invariant. I can also look at the difference between C+ and C-. This goes under the name of spin Chern number. And the spin Chern number, even in systems without conserved spin, corresponds to a physically measurable quantity. It's actually one of several contributions to the spin Hall conductivity. When SOC is weak, it will be the leading contribution to the spin Hall conductivity. It's not the only contribution when there's SOC, but it is a topological one. So some properties of PSP that are important. The first is that its spectrum is gauge invariant. So even though I have to make a choice of spin direction I want to analyze, once I make that choice, which is something that I can do from the outset, my results are gauge invariant and represent, an actual measurable quantity. PSP as an operator is also local in momentum because the spin doesn't depend on position. And so it depends on momentum only through the projector. We can also show that we can compute perturbations to the spin spectrum order by order when we perturb the Hamiltonian, and the spectrum of PSP is well behaved under perturbations. It's also odd under time reversal symmetry and even under inversion symmetry. Maybe a tangential observation is that if I have a 3D TI, the PSP spectrum has to have gapless points somewhere, and these gapless points are like Weil nodes. The way to see this is I can think of a 3D TI in momentum space as a plane at kz equals 0 that's equivalent to a 2D TI, and a plane at kz equals pi that's equivalent to a trivial insulator. Since this plane is a 2D TI, it has partial Chern number C+ equal to an odd integer. This plane has partial Chern number C+ equal to an even integer. And the only way that this C+ can change is if a gap closes in the spin spectrum at a Weil type degeneracy. Okay, so let's use this spin resolution technology to analyze our 3D helical higher order TI. So we can take our projector onto our occupied energy bands, and we can look at the spin band structure. And if the spin band structure is gapped, then we can compute the hybrid Wannier centers for just, say, the upper spin bands. If we do that, we get that they fall into two groups, again, centered near the origin and the boundary of the unit cell. And now we find that for these spin bands, the spin bands near the origin of the unit cell have Chern number ±1. The spin bands at the boundary of the unit cell have Chern number ±1. So this tells us that our layer construction for a helical HOTI here can actually be refined in two ways when we consider the spin resolve topology. Either both of these 2D TIs have the same spin Chern number, or they have opposite spin Chern numbers. The case where they have the same spin Chern number, I'll call a quantum spin Hall insulator, because in this case, the bulk of the system finite size slab has an extensively large spin Chern number. This other case, I'll call it time reversal doubled Axion insulator, because I have the layer construction for an Axion insulator for the upper spin bands and its time reverse copy for the lower spin bands. So these two systems will have qualitatively different physical responses. The quantum spin Hall insulator, because it has an extensive spin Chern number in the bulk, will have an extensively large topological contribution to the spin Hall conductivity in a finite system. This doubled Axion insulator doesn't have a bulk spin Chern number. Instead, it has what we'll call a partial Axion angle for the upper and the lower spin states. What does this mean physically? It means that if we construct a slab of a time reversal doubled Axion insulator, using the same logic we used for the magnetic Axion insulator, we get 0 spin Chern number in the bulk, but we actually get odd integer spin Chern number on each surface, which we can confirm by computing the layer resolved spin Chern number in a model. So odd integer spin Chern number is incompatible with a gapped isolated two-dimensional system with time reversal symmetry, which always has even spin Chern number. So the surfaces of this doubled Axion insulator are actually anomalous. They carry anomalous halves of a 2D TI. And this manifests in terms of a surface topological contribution to the spin Hall conductivity, a novel sort of spin magnetoelectric effect, where applying an electric field induces a spin, or applying a magnetic field induces a spin polarization between the two surfaces. And also magnetic fluxes bind spin-ons in the system, in these systems. So just to give some outlook and sort of broader perspective for what we did, the quantum spin Hall insulator and the doubled Axion insulator, they're the same topological phase in the ordinary sense. They have the same symmetry indicators, can deform one into the other without closing an energy gap. But I can't deform one into the other without closing a gap in the spin spectrum. To go from one to the other, I have to go through an intermediate sort of spin vial semi-metal phase. This suggests that what we can do is view spin-resolved band topology as a refinement of ordinary band topology. Can talk about spin-stable topological phases, which are phases that can't be deformed into each other, which are two spin-stable phases are distinct if they can't be deformed into each other without closing either an energy gap or a spin gap. So these really band topology protected by two different kinds of gaps. Just as a proof of principle, this spectrum of PSP and its topological invariance can actually be computable from ab initio calculations. We did this for candidate higher order topological insulator beta MOTE2 and found that it is in this spin vial semi-metal regime. So there's several open questions and directions for future research here, I think. One is to find material candidates for these doubled Axion insulators. Also, this idea of a partial Axion angle and a surface anomalous halves of 2D TIs on the surface suggests that there should be some interesting field theory for the anomalous surfaces of these doubled Axion insulators. Also, spin is not that special in this framework. What was important about spin was that it didn't depend on position and that it squared to +1. So we can actually extend this to other observables that have these same properties, like layer or valley degrees of freedoms to analyze layertronic or valleytronic responses. We also focused so far on just the simplest inversion symmetric higher order topological insulators, and we can try and extend some of these techniques to this further zoo of topological crystalline insulators, and also to interacting systems where the spin Chern number also has a formulation in terms of twisted boundary conditions. So just to conclude, all of these chiral high order topological insulators are magnetic Axion insulators with quantized magnetoelectric response and anomalous half Chern insulating gap surfaces. Helical HOTIs can realize one of three distinct spin-resolved regimes. In this doubled Axion insulator regime, they have quantized partial Axion angle and anomalous half 2D TI insulating surfaces. And in finding this out, we introduced a new refinement of band topology based on the projected spin operator. So thank you all for your attention, and got close to the right time, but happy to take questions.
Great. Thank you, Barry, for this very nice talk. I really enjoyed how clear you are from the start to the end. That's a very tough thing to do because there's many subtle points in here. I have a lot of questions that I think we'll address during the question answer session. So what I'd like to do is kind of thank the audience for also being here. And thank you to Satwik for organizing this. And let's all take the opportunity to thank Barry once again for this very nice talk. So Satwik, you can go.